My name is Zach Metzinger, N0ZGO. I am one of the board members, but I'm also an engineer on the golf program. And I'll be talking today about our aspirations for microwave on golf. So as soon as they get me set up here, I'll start talking. There we go. Let me make sure this thing actually works. There we go. Excellent. Okay. All right. I'm one of those guys that likes to walk and talk at the same time. I hate being up there. So again, thank you all for attending the 41st Annual AMSAT Symposium. And I'd like to talk to you about our microwave efforts on golf. So a quick background, a lot of you may know this, some of you may not, just depends on how long you've been around. AMSAT was founded in 1969. It was the follow-on successor to Project Oscar, which were just a bunch of guys that wanted to put amateur radio in space. And Oscar is standing for Orbiting Satellite Carrying Amateur Radio. So we have a lot of successful and some not so successful satellites in orbit. AO7 was launched in 1974, which makes it 2 years older than I am. And it's still the oldest satellite of our fleet that is still in operation and can be used. I had to clarify that one. We have over 4,000 members as of the 1st of this month. And we have sister organizations in many other countries. We have some representatives of those here. AMSAT Switzerland, Mr. Michael Lipp. We also have AMSAT UK, David Bowman, which I don't know where he is sitting, but he's around. Oh, there he is, over there. And I don't know if we have anybody else, but those are the two I know who are in person. So it's not just us here in North America, it's everybody. We have had growing ambitions from the start. This is Lance Jenner, this gentleman up here, and that is the first amateur radio satellite right there that he's got under his arms. So those first satellites were the size of shoe boxes. The weight and the size really weren't the driving factor at that point because we were all either on a ride that was high risk, they were testing out a new vehicle, or somebody knew something, or somebody knew somebody, and they were looking for ballast. They were looking for a mass, and it didn't have to just be a lead weight. It could be something useful. But again, we wanted to get bigger, and bigger is better, right? So we kept developing satellites, and the biggest one to date was AO40. It was a multinational cooperation between a lot of different groups. It came in at 4,758 kilograms. And for us English guys over here in the U.S., 10,489 pounds. It had antennas galore on it. We had L-band, S-band, and C, X, VU, and K-bands, and a couple of thrusters. Unfortunately, one of those thrusters was the demise, or actually the fueling system was the demise of AO40. But we had to adapt to the times. So this is the incredible shrinking satellite. So the CubeSat form factor, just as a quick background, a 1U, which is a 10 by 10 by 10, became necessary due to the rising costs of launches. It was enabled by consumer electronics. Everybody wants smaller, faster, better battery life on their cell phones, so it led to the use of a lot of SMT, surface mount technology. And out of this, all of these factors, we got Fox 1, which was AO85, or is AO85. First of the AMSAT CubeSats with a UHF VHF crossband FM repeater, coiled antenna wires that popped out, and that was your antenna. And then there were some successors that were launched. AO91, Fox 1B, RadFX Sat, which is still very usable but can be intermittent. AO92, or Fox 1 Delta, which I've been told just as of this week has started to show some signs of life, which is interesting. So maybe useful. And then AO109, Fox 1E, RadFX Sat 2, which has sort of a very low power linear transponder and very low power telemetry. It is usable, and people have used it. The telemetry, you got to have a big dish, and that's a big antenna right there. That's Dwinglow. Yeah, Burns has to correct me on that one. There have been some, I guess, a lot of FT4, a lot of digital mode contacts through that, some CW, and I've heard people actually running sideband through it. So you can think of it as the weak signal practice for your antenna farm. Not listed up here are a few that went up, didn't quite work, and now are either inactive or have decayed. But we're glad for their service. Again, getting back to microwave ambitions. So since the earliest of AMSAT satellites on AO7, 2.4 gigahertz beacon, which was never activated because there were issues between the time it was built and the time it was launched. The band plan changed, the allocations changed, and we couldn't turn that beacon on. But it's up there. AO10, the 23 centimeter transponder to the 70 centimeter downlink. And then, of course, AO40, many bands from 2 to 24 gigahertz. David Bowman gave me a nice picture. Let me use this picture. This is a AO40 setup that was done for a de-expedition to, you'll have to remind me, David. Rodriguez Island. So this was your background, your backyard? Yes. Okay, so it's being tested in David's backyard. You know, microwave is easy, sort of. Yeah, the antennas are smaller and more portable. The horn type feeds simplify pointing in exchange for lower gain. You'll get pluses and minuses. Oh, you need a dish. Oh, you don't need a dish. I'm not going to get into that. But the CubeSats, we want to get into microwave as well. So on AO92, Fox 1D, there was something called the L-band downshifter. And that's a 23 centimeter converter. So you're listening on 23 centimeters, and it's actually rebroadcasting that to the 70 centimeter, which is then going back into the transverter and coming down on 2 meters. And what's nice about this is you didn't have to modify antennas. You didn't have you didn't have to add extra antennas, and you didn't have to modify the transponder. So it was a nice experimental add-on that I think was pretty successful as far as I know. And Burns and Jerry are both nodding their heads back there. So now we come to Golf, greater orbit, larger footprint. So this is a successor to the Fox series of CubeSats. It is a larger satellite. It's a 3U. So you've got 30 centimeter by 10 by 10. It has a lot more stuff inside of it. So even though we've gotten a lot bigger, we're still facing some of the same challenges. We have a couple of really neat things that go into this, and I think Jerry's going to talk a lot about Golf. So I'm really just going to focus on the microwave portion of it. But Golf T, as being the technology demonstrator, the first in the series, headed toward LEO. Golf 1, all those advanced capabilities after they're tested, they get turned on for general use, and nothing's written in stone. Maybe T works great, and we turn it on for everybody. It's also going to LEO, but possibly MEO. The problem right now that we're facing, orbital debris regulations, and that really threw a wrench in everybody's plans when those came in and said, hey, you can't have these things just up there indefinitely. You've got to move them, you've got to deorbit them. So we're still working through that, but not a complete game stopper. It's just something that changes it a bit. A quick architecture overview, and I'm not going to go into this in detail because, again, I think Jerry's got a lot of this. He's going to go through some of these systems. But just to give you an idea of what we're going to focus on for the next couple of slides, we've got our 10 gigahertz downlink up here. We've got some antennas that go from VHF all the way up to L-band, all the way up to C-band. And then we have a software-defined radio. We've got some other interesting stuff in here that I'm sure he'll talk about as well. So a quick fun fun picture that was taken of one of the development units. This was done by, I believe this is Don Corrington, right, is AK2S, right? A2KS? AK2S, yeah. So this takes all the antennas, pulls them in, turns it into a matrix that then can be fed into that SDR. And then on the other side, when we're coming out of the SDR at 10 gigahertz, we've got the SSPA, and this was done by Bruce Herrick and John Klingelhofer, I believe, are the two that did this board. So we've got hardware in hand, and it has been tested and seems to work just fine. The SDR is the piece of this that really handles all the microwave traffic. This is based around an E310. May have changed since this slide was created, but that was the one we were using at the time. Downlink is centered around 10.4 gigahertz. The peak power into the transmit array is about 1 watt. On Golf T, this will be primarily used for engineering data. So we don't intend it to have user traffic right away. Now, if it's wildly successful and everything works just as planned, we might have user data coming down on this too. You might be able to go up on 2, or go up on, up on 2 and down on 10, which would be really awesome. But future missions plan to open this downlink for user traffic. We have a multi-band antenna, and the gentleman that did this for us, Kent's multi-band antenna, is a space-optimized design. Covers a whole bunch of bands, all the way from 70 centimeter up to 6 centimeter, and also does GPS L1 and L2, just in case we want to put a GPS on the thing and see where we are in our orbit. It does work best when it's pointed at Earth. He'll say it's omni. Yeah, okay, great, but doesn't an antenna work better when most of the patterns pointed the way you want it, not off into space? So I'm not going to argue with him on that, but that is one of the reasons that we put the ADCS on Golf, is so we can orient ourselves and point the antennas toward Earth for maximum gain. So what does it take to get a golf station or a ground station for Golf? It is very similar to AO100. So you've got the your usual UHF VHF capabilities with any sort of CubeSat that we've put up so far, 2 up and 70 down. But you can also get an X-band converter that's a 10 gigahertz model. They're available on eBay. I think Kent said that the latest models are $5. It's absolutely nothing. You're going to put that into your SDR. It's going to come out on some frequency, and off you go. They're very cheap because they're very popular in the EU, and you can't use the ones for Dish. You can't use the ones for the US because it's not the right band. It's not the right frequency range, but they're very, very easy to get, very, very cheap to get. When we launch Golf 1, what are you going to need? Well, you're going to need the downlink, the down converter for the downlink, and then you're also going to need a transmitter that can transmit on one of the uplink frequencies. You can either use a rig that can do 23 centimeter natively, or the 1.2 gig, transverters, and typically you're going to need a power amplifier of some sort. This is where the 2.4 uplink to QO100 is kind of in the right spot, because you've got a lot of, let's say, eBay amplifiers that you can buy for real cheap that are supposed to amplify your Wi-Fi, even though you're not supposed to do that as a non-licensed user of the Wi-Fi. But it's great for us because now we can buy this cheap stuff that works on 2.4. You build yourself a helical antenna. Well, okay, Kent. All right. Well, Kent's going to give you his presentation later and tell you why I'm wrong. But PA1EW has had a success with a nice dish and a helix right here. So, and a GPS frequency reference for your uplink, because even though on the downlink, and I forgot to mention this, let me go back to this picture. If you notice, there's something highlighted in green right here. Ray Roberge, who is responsible for a lot of what the SDR does, the programs that run on it, which are all GNU Radio, he's provided a CW tone for the station, the downlink, so you can lock to it. If you think about it, Doppler gets worse as you go up in frequency. At 10 gigahertz, that signal is just moving. So you want something that aids you in tracking the downlink. That's why he put the CW tone there. So your software locks to the CW tone, corrects the frequency, and then can demodulate everything else. All right, so getting close to the end here, but how do I help? If you have terrestrial or EME microwave experience, and I know we have some people in this room who have done that, get involved. Talk with satellite operators about Doppler, fading, all the problems that they encounter with satellites that go all the way up to, let's say, 1.2, or even those who have worked at AO40 on the higher bands, and create how-to documents, websites. For instance, equipment. What is WR90? Well, it's a waveguide. Well, nobody knows what that is, but maybe you can help explain it to them. Test procedures. How do I know it's working? Well, usually you can put your rig on a tripod and aim it toward a beacon. So continue to provide beacons and ground testing events. The pictures here, actually, the left one was an event out at NTMS, the North Texas Microwave Society, that occurred last weekend, out at Bob Strickland's ranch. Actually, Bob is in the audience somewhere if he raises his hand. There he is right there. Graciously let us all go out there and test our microwave stuff. Not me, I have no microwave. But a lot of great rigs out there, a lot of great setups, and I always learn a lot every time I go. Al Ward and John Schroeder, is that right? Yeah, Schroeder, doing some alignment on a dish out there. So these are the types of clubs that you want to get involved with so that you can gain that microwave experience you're going to need for the next generation Golf satellites. Future directions. Consumer devices are driving the use of microwave bands, which is great for us, good and great really. Cheap, highly integrated surface mount technology devices. But spectrum is money. So commercial interests will continue to ask for more, including our allocations. And the prime example is 3.3 to 3.5 gigahertz. We must utilize it and show that it's being used, or it will be taken away from us. And finally, AMSAT is committed to microwave on future satellites. We'll keep looking up in the spectrum, even to millimeter wave. With that, thank you, and I'll take questions.
Okay, my question is, the antenna you showed with GNSS on it just covers L1 and L2. When L5 is a civil signal, also at 1176, you all should be considering that very strongly.
Okay.
Is my suggestion.
Okay, yeah, and that's something that maybe Jerry needs to hear as well. If Kent, I think Kent actually left the room. Oh, there he is. Kent, what do you say to L5?
Hold on, let me get him a mic.
Oh.
And then I'll bring it back to you.
The antenna is continuous coverage from 1 gig to 26 gig.
So it sounds like 1 gig to 26 gig continuous coverage. That ought to take care of L5 for you.
Okay, well that's good, because and Jerry's asking me on the side, why L5? So about 15 years ago, the GPS community decided to incorporate L2 was primarily a military signal.
Correct.
And the idea was to have a civil signal, which is what L5 is, and it has safety life considerations too. But the most important thing is that it is a pure civil signal. It's wider and can provide more accuracy. So there's a lot of reasons why it isn't totally in use yet, but by the time you get your satellites up, it will be, and I think you need to consider that now. And a lot of the GNSS receivers have that embedded in it. So it comes for free. Just need to make sure you have it accommodated, because if you don't do it now, it's going to be a long time before you have it. It's all in the GNSS receivers that you can get. I mean, let me just say, the real inexpensive GNSS receivers that are flying in CubeSats have that in there. And not only just GPS, but also Galileo.
Okay, well, thank you very much. Any other questions? Oh, I think Kip here in the front.
Okay, now, from what I understand, this is a directional antenna, and it'll be pointing in the -z direction. And how much time in an orbit will we actually be able to see this, and how many times will it be seeable in the United States?
That is a good question that I do not have an answer to, but Jerry and or Kent may be able. Actually, Jerry, look at Jerry's. He's just begging to answer this question. So, actually, since you guys are coming up right after me as part of this, why don't you just come up to the front here, Jerry? And then Kent can speak from the back, please.
Whenever the bird is above the horizon.
Kent with his ever helpful commentary. You can't see it when it's behind the earth. Do you have an answer to that? What do we do? Okay, so I think, yeah, repeating the question is, what's the window? What do we think the window on a typical pass would be for microwave operations. Is it? And go ahead and get that microphone to him, please. Yeah, just the availability. Maybe I'm sorry. Which gentleman asked the question? Oh, Kip. Kip, would you restate your question one more time? Give him that microphone, please. So we need two microphones.
Okay. From what I understand, this is more of a directional antenna. It'll be on the Z minus side of the thing, and we're trying to be pointing at the sun all the time. So that means Z is not necessarily pointing towards the Earth. Mm-hmm. So the question was, how often will it be in a position where we can see it somewhere in the United States where we are?
Okay.
All right, we're gonna let our VPE answer that question.
In general, with Golf T starting up, that's purely to explore the technology, and the SDR is part of that. The X-band downlink antenna at the -Z has to be balanced with the sun we need for the solar panels, which we're not really sure what the trade will be to find. It's too close. Sorry about that. What the trade will be between finding how much sun we need, how much power we need, solar power, versus the angle of the antenna for the 10 gigahertz down. However, the 10 gigahertz down is pretty broad beam width, I understand. So it should be not necessarily having to point directly at you, depending on your ground station. If you've got a, really narrow beam width there, then that'll have to work with it. So of your 10-minute, typically we're going to be at like 500, like maybe 12, 15 at most minute pass. It's going to go pretty quick, and we intend to use it as much as we can. It'll be data downlink. That's what we have to prove. After that, then we will be looking at adding the voice via repeating the UHF downlink from the transponder.
I'm going to take this.
There's another angle to your question which relates to what I'll call pointing control. And one of the modes that we are confirming that our ADCS supports is what I'll call pointing, say, to Earth, and then best effort rotation of the panels toward the sun. So one of the possible modes is you keep the Z pointed to Earth at all times, and then do the best you can to get the maximum power out of the solar panels, depending upon the orbit. So there's those kinds of plays that we're messing with from a control standpoint.
One thing to add. We don't know what the orbit will be. We know what we asked for, but we, being hitchhikers, when it comes along, it may be sun sync, it may not, and that makes a big difference actually. So we'll have to see what that is to make a final determination.
Okay, we've got Kent's got a question or a statement from the back there.
This is not the X-band transmit antenna. That'll be in my talk tomorrow. But the X-band is a patch array. It's aimed back at the Earth. Its pattern is roughly so that the width of the beam is equal to the width of the Earth.
All right, thank you very much, Kent. Other questions before I wrap up this section? Okay, I think we will right now. So this is actually part of the AMSAT engineering update. I went first, so again, I'm Zach Metzinger, N0ZGO. Jerry Buxton is up next, VP of Engineering. And Jerry, I'll get your slide set up for you in just a second. So warm round of applause for Jerry.
I'm Zach.